Thanks, everybody. Thank you for turning up to my talk. It's great to be here. When I accepted the invitation from Ernie and Fenella a while ago to speak, we settled on a topic of the geology of the solar system, which at the time seemed like a great idea, because I'm one of the few faculty who study planetary science full-time at NC State. It's a relatively new topic we're developing there. When I realized that I would only have 30 minutes or so and not 3 days, I figured that the geology of the solar system was maybe not such a good idea. But in the next 30 minutes or so, over the next 30 slides, I'm going to try and condense 50 years of spacecraft exploration of more than 24 bodies that are more than 4.5 billion years old, to try and at least give you a flavor of the type of geology we see, the types of landforms and processes present throughout the solar system. So this is a model of the solar system that I grew up with. In fact, when I was a kid, there was number 9, Pluto, and that's a whole separate issue as to why it's not on this picture. And I don't particularly agree with that decision, but that's not my call. But nominally, the solar system consists of 8 planets, right? And we all grew up with mnemonics to describe this. And when I was a kid and I was growing up, that growth chart, was the solar system for me. And I think I hit Pluto around 7 or so. It turns out that that's not really an accurate representation of the solar system. The solar system is sort of made of these things plus a whole pile of other stuff. And some of that stuff we've always known, but we've never really given much attention or credence to. We've assumed, for example, things in the main asteroid belt are all the same, and they're vastly different to each other. Or there's things that make up what we call the Kuiper Belt, which is this region of bodies way, way far out. I mean, it's difficult to be superlative in describing how far away this stuff is. And even farther again, something called the Oort cloud, which we only think by theory is a real place where comets are born and where they come into the inner solar system and take thousands of years to do so. The take-home message is the solar system is far more complicated and sophisticated than we've ever thought it would be. And on every mission after mission that NASA or ESA or the Japanese or the Russians have sent somewhere, you see scientists on the news express how surprised they are. Oh, we didn't think it would be this interesting. And yet after the 15th time that happened, surely we should stop being surprised. Because our models generally are very one-dimensional to explain how planets get made and what they do and what they look like. And so when we go and realize just how varied they are, we need to realize these things are very sophisticated systems and they defy our basic explanations for how they get made. So that's one of the strengths of understanding the solar system through robotic spacecraft exploration, is that we are getting a much more detailed view of the rich tapestry of stuff that exists out there. And that tells us a lot about our own planet as well. So for this talk, I'm going to take sort of the greatest hits, and in fact I'm omitting most of the interesting stuff for the interests of time. But I'm going to show you some of the most recent discoveries we have from spacecraft missions, including some landed missions for bodies throughout the solar system. Even just to illustrate a small part of the gamut of diversity and interest in the solar system. As I say, we've got 50 plus years of solar system spacecraft exploration, and I don't expect anyone to be able to read any aspect of this infographic. I'm showing it only to illustrate the fact that we have sent a whole pile of stuff to a variety of bodies in the solar system. And you might notice this is the moon, and each of these individual lines, of which there's legion, indicates a single mission that has gone to that body. We've sent loads to the moon, quite a few to Mars, quite a few to Venus. We've only visited Mercury once in terms of orbit, but we did send one other spacecraft there, and the European Space Agency is preparing to launch a third. We've got some really flagship missions out to the outer planets, to the giant planets, which Jupiter, Saturn, Uranus, and Neptune. And you may know, if you're interested in this topic, that NASA's Cassini spacecraft met its fiery end a little under 2 weeks ago. And it did an amazing job. Cassini launched in 1997. It took 7 years to get to Saturn, but operated there for 13 years and has revolutionized our understanding of not just Saturn and its rings, but Saturn and Jupiter have so many planets, you can almost think of them as mini solar systems. So that really has opened our eyes to things. And of course, Cassini was crashed into Saturn to avoid even the remotest possibility that any life from Earth might still be extant on that vehicle. And by avoiding the risk of crashing into Enceladus or one of the other moons that may actually harbor life itself. And I'm going to illustrate some of those moons in a few minutes. So the point is, we've had a lot of time to explore these bodies. And I think now we've pretty much hit all the major ones. But that just means we have a first-order understanding of these worlds. I tell my students that we've had 300 years of geology as a scientific discipline, and we understand perhaps the first 10 kilometers of the land part of this world, maybe going back 300 million years, which is less than a ninth of the age of less than the 12th of the age of the planet. So we think we understand Earth so well, and by comparison we do, but we don't really. And we certainly don't appreciate that Earth has changed fundamentally as a planet over the last 4.5 billion years. So when people come, and people like me, come and tell you these grand sweeping statements about Mars, please have a little kind of star beside any statement you could ever hear a planetary scientist tell you, because we don't really know. But we can tell you the basics. We can tell you the important, basic, fundamental stuff. I'm going to start from the inner part of the solar system and work out, and I will try to do so as quickly as possible. It is entirely likely that I will go down some random rabbit hole of facts, which may be interesting, but will inhibit me getting to the end of the talk in a timely manner. So I might ask you just kind of keep an eye on the clock and tell me if I'm going over. But I feel I'm going to start with Mercury for a couple of reasons. One, it's the one closest to the sun. And two, I have a particular kind of affinity for this world because I worked on NASA's Messenger mission to Mercury, which was the first spacecraft to orbit Mercury. In fact, although we'd visited it with a spacecraft called Mariner 10 in the 70s, we as a species didn't know how to get into orbit of Mercury until 1985. We didn't have an explanation for how we would do it with a plausibly sized spacecraft. So in St. Patrick's Day 2011, the Messenger spacecraft, which isn't much bigger than this podium, entered orbit for Mercury for the first time, and over 4 and a bit years imaged the entire world, and told us that it's a fascinating place, very unlike the moon, which is what we had thought it would be the case before we visited there with Messenger. It's a heavily scarred world with many impact craters, but one of the things we discovered with geophysical measurements with the spacecraft is that you can consider Mercury as essentially a giant molten ball bearing that happens to have a little bit of rock around the edge. This is a kind of a stylized cartoon cross-section. All the yellow is the core. It's the liquid outer core. It generates a magnetic field for Mercury. This is essentially what we would call the mantle. And then this thin line would correspond to the crust for Mercury. Now on Earth, the ratio of this rocky stuff to the iron stuff will be somewhere here. It's about half. So it's strange, and we don't have one good, definitive, satisfying answer as to why Mercury happens to have such a gigantic core. But it is the largest uncompressed density of any of the planets in the solar system. It's essentially a molten ball bearing that happens to have a little bit of rock. And one of the interesting geological consequences of this is that it's been losing heat through time. Everything in the universe will do that through time. And like any object that cools down at night, like your house, or a wedding ring on a finger at the end of the day in the summer, stuff contracts as it cools down. And in fact, Mercury has contracted. It's squeezed in or shrank under its own weight. And as a result, we have these towering cliffs, essentially mountain ranges that run across the surface. This is a portion of a landform we call Victoria Rupees. And in this picture, looking down, the sun is shining from the top of the picture. So these are impact craters. Sometimes people have a hard time and they might look like domes. They're supposed to be impact craters. And this shadow here tells us that this part of the land here is elevated with respect to that bit of land there. This thing is so big. The field of view in this picture is about 250 miles or 400 kilometers. It's part of a system that's almost 2,000 kilometers long. I just can't fit it in the screen properly. And this whole region of this chunk of crust has been pushed up and over this bit here. We think because just like a prune that dries out, as Mercury is cooling and contracting, the crust is being pushed up on top of itself. We call this process global contraction. It's likely affected everywhere, every solid body in the solar system, including Earth. Except on Earth, plate tectonics makes it very hard for us to deconvolve that other signal. But in the case of Mercury, it's produced these dramatic cliffs right away around the planet. Even relatively young volcanic plains, which don't have these towering cliffs and mountain ranges, still have this weird wrinkly pattern. In fact, we call these things wrinkle ridges. And the best way we have to explain their formation is that these big oceans of lava that get poured in extremely fast, much like the lunar maria, the bits that make the dark splotches on the near side of the moon we see at night, they're emplaced very, very fast as lavas. But then as they cool down, the planet starts to squeeze in on itself again, and you get these wrinkles. Now, we see similar landforms on Mars and the Moon, but it was dramatic just how many of them and how big they are on Mercury. So that's giving us a good understanding of what a small rocky world does, particularly as we begin to understand exoplanets or extrasolar planets in other star systems. This is going to act as a template for us understanding these other worlds. Venus is one of my favorites. In fact, arguably, they're all one of my favorites. But Venus is particularly interesting from one angle. Venus is Earth's sister planet, but it's not its twin planet. And we don't yet have a good understanding of why that is. Venus is about 90% the radius, happens to be about 90% the mass, so the gravity is about 90% the gravity in this room. You wouldn't feel very different. You could jump a little higher. Now, you'd be dead, because the surface pressure is about 90 bar, which is the equivalent of about a kilometer under the ocean. And the temperature at the surface of Venus is that of a self-cleaning oven. So this is why we've only ever landed stuff there a handful of times. In fact, the United States has never successfully landed something on the surface of Venus. The Soviet Union did a few times. They had a number of what we call the Venera landers. And the Venera landers managed to take some photographs of the surface, which I'll show you in a moment, The Venera landers, I think, represented Soviet engineering ingenuity because they launched a whole pile of them, most of which didn't work. And when one didn't work, they just launched another one. And eventually, one of them landed, and then, okay, the first one that landed fell over as soon as it got there, but it did actually successfully land. The second one had big metal discs over the cameras, which were pyrotechnically jettisoned. And there was a hammer on board the spacecraft designed to measure the strength of the rock. And of course, for the second lander, they jettisoned the camera image, or the camera lens cap, this steel plate, on which the hammer immediately slammed into the plate, returning them evidence for the strength of the metal, which they'd made in their same lab. But the third or fourth, or possibly sixth lander actually worked, gave them some strength values, took some radiation samples, and it returned some images of this surface. But there is a compelling reason to go back to Venus, because it's a planet just like ours, around the same star, made of the same stuff, but is vastly different. In fact, you can't see very much from space because the clouds are thick carbon dioxide and sulfuric acid clouds. But if we use radar from, say, the Arecibo telescope or NASA's Magellan mission in the early 1990s, we get a vastly different world. There's no evidence of plate tectonics here. There's no evidence of oceans. If we look at the topography of Venus, in this case, blue is low and kind of red is high and green is intermediate. There are these two elevated regions here and here, Ishtar and Aphrodite Terra, that some people think might be continents, made of the same stuff that our continents on Earth are made of. We don't see that material anywhere else in the solar system, but we don't know for sure what this is made of because only one Venera lander touched down around there and couldn't definitively tell us. Why does a planet, it's essentially the exact same as Earth in terms of its bulk composition and proximity to a star, look so different and have such a vastly different geological history? We do not have a satisfactory answer for that question. But there's a possibility that Earth is going to endure a similar fate as Venus at some point in the distant future. Or, if we're talking about looking at extrasolar planets someplace else, if we find an Earth-sized exoplanet, and we talk about, oh, maybe it's habitable, keep in mind, this is an Earth-sized planet orbiting the habitable zone of a main sequence star. And no one would look at Venus and think, oh, we're going to go land there, because you'll die. So this is an important thing for us to understand. Why is this so different? Why is it our sister, but not our twin? These are the two pictures from two Venera landers that show you what the surface is. Sort of color corrected. But we see very smooth, expansive lava plains, and in the distance, some sort of hills. And you can kind of see the sense of kind of like a mist or a fog in the distance, purely by virtue of the atmospheric pressure. But these landers only operated for about 90 minutes before they were essentially boiled and then crushed. But right now, I have colleagues at NASA Ames and NASA Marshall who are trying to develop transistors that are able to withstand these temperatures and pressures for months at a time. So it may be within the next generation, we will have landers and even rovers on the surface of Venus that will enable us to properly explore this hellish planet. I'm purposely skipping Earth because we can talk a lot about Earth, that's easy. Next one out is Mars, the red planet. And Mars is a fascinating world. And what's interesting is Mars has sort of heralded in the new golden age of NASA exploration with the Sojourner mission in 1996. This little thing about this big, much bigger than a shoebox that drove around the place. And that led the way for the Spirit and Opportunity rovers and now the Mars Science Laboratory Curiosity rover. And its twin, Mars 2020, will launch in 3 years' time. And it may even cache some rocks that we may eventually bring home. It's easy to forget, in the light of all this successful exploration, that was also joined by the Mars Reconnaissance Orbiter, the MAVEN Orbiter, the Phoenix Lander, that until the mid-1990s, getting to Mars was extremely difficult and fraught with a high likelihood that your spacecraft is either going to crash in or otherwise not make it. In fact, Mars Polar Lander and Mars Climate Orbiter are two examples of spacecraft in the early to mid-90s that were sent and they did not successfully land on Mars. But in the last 20 years, our understanding of this world has changed dramatically. And I'm only going to give you sort of the greatest hits. I have a particular affinity for volcanoes. That's where I study for my PhD, these giant volcanoes. This is Olympus Mons, the biggest volcanic edifice that we recognize in the solar system. Olympus Mons is about the same size as Arizona. And it's 22 kilometers tall from stem to stern. In fact, it's so big that if you were standing on the base of the volcano, you wouldn't know you're on a volcano because the summit would be over your visible horizon. It's that big. And there happen to be 3 other gigantic, but slightly less gigantic volcanoes that together make the Tharsis Montes. Understanding why you get gigantic volcanoes on Mars is important, probably tied to the fact that unlike Earth, Mars does not have plate tectonics. So when you have a plume, which is basically a tunnel or a chimney of molten material from deep inside the planet, on Earth, we get these volcanoes that make up, say, the Emperor Seamount or the Hawaiian Islands, because this plume is stationary, but the plate moves over. If you don't have a mobile plate, you can just sit there and build up a lot of lava over, in some cases, 3.5 billion years. So we get this planet that's about the size of our outer core, right? Compare Earth, Mars. But it basically has these superlative landforms. It has something called Valles Marineris, so the Valley of the Mariners, which is basically the width of the continental United States, and in places 12 kilometers deep. So the Grand Canyon, yeah, it's impressive, right? And we're going to go bring a bunch of students there next week for our fall break trip. But I'm going to remind them that the Grand Canyon is one of these small little things here that you wouldn't even bother mapping compared to this thing. But then equally, the Grand Canyon is about 6 million years old, and this thing is 3,500 million years old. So it's had a bit of a head start. But these are the kind of landforms we see on our neighboring planet, and they are fascinating. And understanding how they form tells us not just about how Mars evolved, but also how planetary bodies like Earth evolve in general. To say nothing of the fact that NASA has become extremely media savvy. The reason this thing, Mars Science Laboratory, which is the size of a Mini Cooper and is nuclear powered, the reason it takes these selfie pictures is so that engineers can ensure that the wheels are in okay shape, that a lot of the instrumentation isn't covered in dust, that they can know how the machine is getting on. But they release these selfies and it looks for all the world like this thing just drives around snapping pictures of itself on Mars all day. But there is an engineering reason for it. However, this thing, through NASA's media PR outreach, has revolutionized a new generation of people understanding why we fly these things and put them on other planets. Now, I wish I had time, I don't, to show you the video as to how this thing was landed on Mars. But if you don't believe me, go later on to YouTube and type in MSL Sky Crane and watch a video called 7 Minutes of Terror, and it will tell you what JPL is capable of doing in terms of getting a nuclear-powered tank the size of a car onto the surface of the red planet. Now, at this point, about 5 or 6 years ago in this kind of talk, I would skip ahead to the satellites of the big planets, because they're really interesting, and I'll get there in a moment. But in the last 10 years, we've had this kind of revolution in terms of understanding just all the smaller bits that are left over after the big planets formed. Now, when I teach my planetary science class, I kind of use an analogy. If you've ever built a Lego set, or built a bed or a bookcase in IKEA, at the end of the time you're finished, you have all these random bits left over, like a dowel and screws, and you're like, what in the hell is this for? That stuff is comparable to what we call the asteroids and the comets. Because this stuff was never enough, and the unique history of these objects, they never got made into or subsumed into things that went on to become the planets we recognize today. So they're still there. And they're incredible to study because they are basically stuff that tells you what the composition of the solar system was 4,500 million years ago. We have no way else of finding this stuff out. This is comet 67P, Churyumov-Gerasimenko, or just 67P because that's difficult for an Anglo like me to say. But the take-home message is this thing is only 4 kilometers across, but it's a fascinating comet. And ESA's Rosetta spacecraft visited there successfully in 2014. And it has revolutionized our understanding of these small things, which until recently we thought were boring. Yet on this world, which looks a bit like a rubber duck depending on the angle you look at it, and is probably made of 2 separate comets that basically were bolted together, this thing started to degas as the spacecraft was following it on purpose. They scheduled the arrival to coincide with this thing getting closer to the sun heats it and begins to degas. There's a movie, Deep Impact, where a bunch of astronauts are sent to blow up a comet. It turns out that's not at all what comets actually look like, but comets look for all the world like they're made of rock. Right, they're dark and they have all these sort of jagged things and they have cracks through them and they've got dunes and they've got steep cliffs, except that it's made of ice, not rock. But we can understand these things with the same techniques and processes and analytical equations that we use for rock, just equally to understand what the behavior of ice here. But this thing is a remnant from the very formation of the solar system. So understanding its chemistry, its internal composition, its geophysical parameters gives us this unique insight and tells us we have to go back to more comets because no two are alike. Moving farther out, you get to the giant planets. And there's 2 giant gas giants and there's 2 ice giants. There's Jupiter, Saturn, Uranus, and Neptune as you go out away from the sun. And I wish I had time even to talk just about these moons. I don't. But I'm going to visit a couple of them really quickly. To scale, this is the curvature of Saturn with its rings as its background. This is a composite image, but it's all real photographs. The single largest moon of Saturn is Titan, which itself is bigger than Mercury. It's only called a moon because it orbits a gigantic planet that's 100 times the mass of Earth. But in its own right, it is a world, and it's a fascinating world. But even the small ones that appear to be relatively geologically inert are fascinating and record such an interesting history of geological processes. But Titan in particular is amazing. Titan is the only other body in the solar system that has an active hydrological cycle. It has rivers and lakes, it has rain, it has erosion. These lakes' levels fluctuate up and down, except that we don't call it a hydrological cycle because hydro implies water. This is a methanological cycle because the temperatures at Titan are so low that methane is the fluid agent. That's what's able to make these lakes and rivers, and the same sort of digitate pattern and fluvial patterns you get in rivers on Earth look exactly like they do on Titan. And it rains there. It rains liquid methane. And then there's sand grains that form dunes and ripples. There's something called the Great Dune Sea near the equator, which is like something out of a Tolkien book, except that those are made of methane and ethane grains. This is an amazing world, and the problem, just like it is for Venus, is we need radar to see the surface. This is a radiogram, not a photograph. But right now, this is the target of 2 additional mission proposals into the most recent New Frontiers class mission competition NASA is running. They're going to make some selections for the next phase of more detailed study in December. And with luck, at least one of them will be one of the Titan missions. In fact, my particular favorite is coming out of the Applied Physics Lab in Maryland. They want to send a drone helicopter this big and fly it on Titan. So that would be particularly cool. It's called Dragonfly. But we're going to find out in December if this is going to be the target of at least one of these more detailed studies. Because Titan is an amazing world and critically may have some what we call prebiotic chemistry that could be similar to what Earth would have had around the time life got going on this world almost 4 billion years ago. Other fascinating places in the solar system, or rather before I go on, this is simply a picture. We did land something called the Huygens probe on Titan back in 2004. And this is a set of images, color accurate images with the blue sky before you get this orangey sort of smog. This is literally hydrocarbon smog. And as the Huygens probe descended, it showed us these pictures. It was rotating slightly as it descended. Huygens is the probe that returned a picture from the farthest landing we've done so far as a species. There's just so many reasons to go back to Titan. This is Dione, a far less interesting world. It has no atmosphere. Its outer surface is made of ice, not rock. Yet it still has impact craters that we can count and analyze their morphology. It is a gigantic tectonic rift cutting right through, a bit like the East African rift in Ethiopia. And we can use the same geological approaches and techniques we use for Africa to understand the formation of this ice shell. And there's lots of other bodies like Dione orbiting Saturn. In this nice picture, by the way, this is a real photograph. You can see one of Saturn's rings edge on up the top of the picture there. And then, of course, diminutive Enceladus. Enceladus is smaller than the north-south extent of Great Britain, like the bigger island where I'm from. So it's tiny. It's about 500 kilometers across, 300 miles. Yet despite that, it has these weird stripes on the bottom we call the tiger stripes, from which water is blasted out from the interior. Because we think there's actually, under this icy shell, a thick ocean. And what's interesting is, not only is water coming out here, it's also organic compounds are being blasted out because they flew the Cassini spacecraft through the plumes. In fact, one of the other New Frontiers proposals is to take a new spacecraft and dedicate it purely to study Enceladus and fly repeatedly through those plumes, sampling them, tasting them, using onboard spectrometers to figure out what they're made of. If you have liquid water, and it's liquid because something's keeping it warm inside, so you have energy, and you have organic compounds, it is thought they are the 3 things you need for life to get going somewhere. So this is a dominant target right now for what we call astrobiological research, to understand if there is life here, and if so, that would have tremendous implications philosophically, historically, culturally, as well as scientifically, for whether or not there's life someplace else in this solar system or in the universe at large. It was particularly to protect this world and Titan that Cassini was crashed into Saturn, to obviate any likelihood that it could crash here and end up contaminating it. Jupiter has 4 very famous Galilean satellites observed by Galileo in the telescopes back in the 1600s. Again, each is worthy of its own talk. Io, the most volcanically active body in the solar system, made of sulfur dioxide and sulfurous volcanism. Europa, which I'll illustrate in a moment. Ganymede, the largest moon in the solar system. Mercury is about this big compared to Ganymede. This is a planet. We just call it a moon because it happens to be around Jupiter. And then even Callisto, what's fascinating about Callisto is these worlds are almost the same size. They orbit the same planet. They should be made of the same stuff. And yet this thing looks like it never had any geology after about 4 billion years ago, and it's half the density of this thing. And we have no idea why you get such a contrast. But it's like Earth and Venus being different, despite having similar neighborhoods. Ganymede is the only moon, and one of 3 worlds, including Mercury and Earth, that has its own intrinsic magnetic field. In fact, although there's an outer icy shell, we think that there's an 800-kilometer thick ocean. Can you imagine? The deepest oceans on Earth are nominally 5 or 6 kilometers. The Marianas Trench is 11 kilometers. There's 800 kilometers of water here. In fact, at the bottom of that ocean, this pressure is so high, you have ice that's 40 degrees Celsius because it's in an ice phase only because of the pressure, which is insane. But under that, you get into proper rock. And it surely has had volcanism. It's essentially the moon with an 800-kilometer ocean. So ESA right now is developing the JUICE mission to go and spend time looking at Ganymede, because this is probably my favorite. But we don't know very much about it because we've only ever imaged it in detail from the Galileo and the Voyager 2 probes. We know so little about these things. It's worth spending a moment just kind of showing you what the surface of Ganymede looks like, because it has these older areas that are very heavily cratered. And when it comes to planetary geology, we typically assume the more cratered something is, the older it is. It's just had more time to accrue a record of cratering. But it has these weird rifts, these kind of colored bands with very few craters, relatively speaking, which are younger. In fact, this almost looks like plate tectonics. Now, whatever this process was, it stopped. But it did operate for a time. One of the compelling reasons to go back and study Ganymede. And of course, Europa. And if you're familiar with the 2010 book that Arthur C. Clarke wrote, or the film of the same name, All These Worlds Are Yours Except Europa, Attempt No Landings There. This is where the monolith was, and it sets up this new life. It happens that in real life, there's a very strong possibility there is an ocean under this shell, and that ocean is probably full of organics. These red cracks are breaks in the ice shell, but the reason they're red, we think, is because there's a red, rich organic material in the water that gets deposited inside these cracks. That's how we know what's inside. Right now, NASA is engaged in studies of what's called the Europa Clipper concept, which is going to be a flagship mission launched in 2024 to orbit Europa itself to actually resolve whether there is an ocean there and to characterize its habitable conditions. In 2025, there may even be the Europa lander, which would in fact make an attempt to land here to try and understand what this stuff really is made of and if there is evidence of life trapped in the ice. That's cool, that's perfect timing. At this point, we're moving farther out again. Now, Uranus and Neptune, each worthy of their own talk. Uranus's moons are incredible. There's a moon called Miranda, which when it was first observed by Voyager 2, looked like it had been broken apart and came back together. Now that's not the leading explanation for the geological processes it has or its landforms anymore. But the fact that the Uranus system was only visited very, very briefly by Voyager 2 in 1989 means that we need to go back there and understand that world because it's enigmatic. But moving even farther out again to Neptune, we visit the largest moon of Neptune in a world called Triton. Now, I've included Triton for a couple of reasons. The principal one is that it's a gigantic moon. It's a planet in its own right. It orbits the wrong way around Neptune relative to all of Neptune's other smaller moons, which honestly aren't that interesting. It's thought that this did not form in situ. It's a Kuiper Belt object. The Kuiper Belt being the next thing you visit after you visit Neptune. We think this thing moved in a very long time ago at a very high angle and a high speed, but was captured by Neptune in the process, either ejecting from Neptune's gravity field the smaller moons that Neptune had, or driving those small moons into Neptune, and it ate its own moons, leaving behind this thing going the wrong way around Neptune relative to everything else. So for a start, visiting here would take less energy, and energy equals dollars, to get to visit than sending a spacecraft to the Kuiper Belt. It's come in a little bit to us. This, again, was flown past by Voyager 2 in '89. Voyager 2 only imaged about 40% of the surface. There's a whole hemisphere it didn't see. And the prevailing wisdom until that point was that the Kuiper Belt objects, there's nothing interesting about them. They're just those leftover bits of IKEA. Except this is a planet with a bunch of different surface textures. Some parts of this have no impact craters, which means that it's at least younger than the formation of the age of the solar system. And you may notice these kind of weird black streaks. Remarkably, there were basically volcanic activity happening, some sort of black material being blasted up in jets off the surface, being entrained in the unbelievably tenuous atmosphere, which was still enough to have some kind of wind. And this material got deposited downwind and then fell out again, making these weird black streaks. We have no idea what this is. We have no idea if there's an ocean there. We don't have enough geophysical measurements to estimate that. We don't know what the back of this thing looks like. But understanding Triton gives us another data point for telling us what the Kuiper Belt is made of and the weird variety of worlds that could exist out there, of which there are probably tens of thousands. And what's particularly interesting is this had been thought to be an archetype for understanding Pluto until we got to Pluto. And it turns out Pluto looks nothing like Triton, but they're both in the same region of space. So you cannot look at one Kuiper Belt object and say you've seen them all. Literally, we have not. This is a composite image, and you may be able to notice this dark thing lurking here in the back. This is an enhanced color, but the correct radiance values for Charon, the biggest moon of Pluto, and Pluto itself. Charon is super dark, right? They haven't enhanced the brightness very much. It's got a weird splotch of red that's called the cappuccino cap. Not that strictly scientific of a term, on the north that we think is what this stuff on Pluto is, and it's stripped off Pluto and then deposits itself on the top of Charon, literally like the chocolate you put on top of the cappuccino. There's this huge heart-shaped region which we think, it's called Sputnik Planitia, it's a smooth area here. We think it's a gigantic impact basin. All of the mountains around here are made of ice because under the temperatures in which Pluto experiences, that ice is harder than granite. And we have big mountain ranges on Earth made of granite. This stuff here is nitrogen ice. It's so cold, it forms a solid phase, but it's convecting and slowly roiling. And if you get the eye and you'll notice, certainly in zoomed up pictures of Sputnik Planitia, there are these weird cellular patterns occurring. We think basically this thing is slowly convecting. There's heat driving tectonic and volcanic activity inside Pluto. It's even thought that all of this is just the manifestation of the icy shell. There's probably an ocean under this, and under that again, a rocky world. So when we think of rocky worlds, we should absolutely include Pluto in that. But it's clear this looks nothing like Triton. So two Kuiper Belt objects look vastly different. The Kuiper Belt itself is probably super varied. For the last minute or so, I want to just comment on the fact that we're using these observations not just to understand these other worlds and compare them, a technique we call comparative planetology, to understand our own world, how we got the way we are, and how we diverged, and how our path has been different to other worlds. But it's also helping us understand extrasolar planets, or exoplanets. This was an image that was released earlier this year from what's called the TRAPPIST system, which was TRAPPIST-1, discovered with the TRAPPIST telescope, named for the monks with the beer. The take-home message is they found subtle astrophysical evidence for up to 7 terrestrial worlds in what's called the so-called habitable zone. The habitable zone conventionally is described as that region of space far from a star where liquid water can exist. It's not going to be gaseous and it's not going to be solid. It's going to be in the liquid phase. And therefore, it's one of the 3 principal ingredients for life. The problem with the habitable zone concept, of course, is I've been talking about how Europa and Enceladus and Ganymede and Triton could have life. They don't fit the easy idea of this habitable zone. But it's a useful place to start thinking. I just want to make the point that although these worlds almost certainly exist, these are nice graphic artist pictures that NASA puts out. We have no idea what these things look like. They could look weird, but you could put almost anything you want onto these things. I tell my students that, certainly as a kid growing up, watching Star Wars and Star Trek, every time someone went to a new solar system, there was this variety of weird-looking planets. But until 1995, we had no scientific justification for ever doing that. That was all art design. It turns out, 1995 onwards, we start finding extrasolar planets. And it turns out now that almost every star we point a telescope to has at least one planet. Planets are ubiquitous. They are the thing that happens. So you can have such an amazing array of diversity and stuff in the universe. But we don't have a good sense of what they actually look like. And there's a risk in putting these pictures out there, or images like this, which kind of imagine what an alien sunset would look like. This is for a world that's thought to orbit Proxima Centauri. It's called Proxima b. It was announced last year. An amazing discovery. Our nearest solar neighbor has at least one planet, probably has several. It's possibly an Earth-sized planet because the technique they use to measure it gives it a value of Earth's mass of about 1.2. So 1.2 times bigger than Earth. But that's a minimum. If it's that value, it's made of rock. And who knows, maybe it does look like this. If it's more than 1.2, if it's 1.5 or 2, then it's no longer a rocky world, it's a gas world. And it absolutely doesn't have a surface that you could land on, and it wouldn't look like this. So what we try and do when we kind of reach out to people through our PR stuff as well, is to at least let's engender an interest and an excitement in the imagination of the public that we are discovering these worlds, and they legitimately, absolutely could look like this. There might even be cities where things are flying around. But we don't know for sure yet because we're still only in the very, very baby steps of understanding these other worlds. However, from what we've seen in our own solar system, I can guarantee you that somewhere in the universe there is a world as fascinating as this. It might not just be next door. I'll finish there and take any questions you have. Thank you very much.